Dr. Ari Siddiqui, we'll start. I think it's good mood. Yes. Assalamualaikum warahmatullahi wabarakatuh. Good morning. Thank you, ladies and gentlemen, for being here this morning. My name is Agus Budi Raharjo. I'm the moderator for this webinar. Today, we are pleased to welcome our two special guests, Dr. Kondakher Solihin from California State University, Dominguez Hills, USA, and Dr. Ari Siddiqui from Institut Teknologi 10 November, Surabaya. They will present their vast knowledge of the domain of computer networks and its application. In this webinar, we will have three main sessions. The first one is the presentation of Dr. Kondakher Solihin, followed by the presentation of Dr. Ari Siddiqui, and the third session is the question and answer. Before we start the presentation, I would like to invite Dr. Iketut Edi Purnama, as the Dean of the Faculty of Intelligent Electrical and Informatic Technology, or we can call it F-ELECTICS, Institut Teknologi 10 November, to give the opening speech. Please, Dr. Purnama.
Thank you very much. Sorry. Thank you, Mr. Agus, and good morning, very good morning. Welcome, Prof. Kondakher Solihin. And for all of you, I say Assalamualaikum warahmatullahi wabarakatuh. Thank you for being in our seminar, web seminar. Here we see the keynote speaker in this seminar, Prof. Kondakher Solihin from California State University, USA, and also Honorable Mr. Ari from Informatics Department, Informatics Engineering Department, Institut Teknologi 10 November, Surabaya. Selamat pagi, salam sejahtera buat Bapak Ibu semua. Terima kasih sudah bergabung di acara webinar F-ELECTICS ITS Webinar Series. Ini webinar dari fakultas kami, webinar yang ke-8. Nah, Bapak dan Ibu, jika Bapak dan Ibu ingin mengikuti terus webinar-webinar dari fakultas kami rencanakan tiap minggu ada webinar series. Untuk minggu depan itu di bidang power, di pengamanan rumah atau industri dari kebakaran, risiko kebakaran. Kemudian minggu berikutnya dari teman-teman sistem informasi, kemudian minggu berikutnya dari teman-teman teknik komputer. I'm sorry, talking in Indonesia, Prof. Kondakher.
That's fine.
Okay. I will let me present about our faculty for maybe for 3 minutes.
Mm-hmm.
Okay. Just to promote our faculty to audience. Okay. Bapak dan Ibu, fakultas kami ini terdiri dari gabungan dua fakultas yang dulunya bernama Fakultas Teknologi Elektro dan Fakultas Teknologi Elektro, kemudian Fakultas Teknologi Informasi dan Komunikasi ya. Bapak dan Ibu, ITS dikenal sekarang menempati posisi ketiga ranking internasional, kemudian secara ranking QS, kemudian ranking Times Higher Education juga cukup tinggi, yaitu peringkat ketiga. Kemudian ITS terdiri dari 7 fakultas, salah satunya adalah Fakultas Teknologi Elektro dan Informatika Cerdas yang terdiri dari 6 departemen. Ini departemen yang ada di fakultas kami, ada Biomedical Engineering, Electrical Engineering, Computer Engineering, Informatics Engineering, Information System, dan Information Technology ya. Kemudian Bapak dan Ibu, total student body kami sekitar 3.300-an, termasuk mahasiswa S2 dan S3. Kemudian akreditasi kami sebagian besar A, dengan total fakulty staff atau dosen sebanyak 175 ya. Bapak dan Ibu, kami adalah perguruan tinggi dengan ranking 1 di bidang computer science ya. Jadi salah satu yang akan dibicarakan adalah sesuai dengan tema hari ini. Juga di pemeringkatan Scopus, dosen-dosen kami menguasai baik di level nasional maupun di level ITS. Ya. Kemudian Bapak dan Ibu, 23 autor dari ITS itu adalah dari 15 dari 23 dosen kami di peringkat Sinta 500 orang itu berasal dari fakultas kami. Kemudian ini kami ingin mempromosikan jalur program pasca sarjana, yaitu program Doktor by Research. Jadi Bapak dan Ibu dosen dari perguruan tinggi, silakan bergabung di program doktor kami. Ada 2 program studi, yaitu di ilmu komputer atau informatika, itu membuka S3, kemudian S3 di teknik elektro. Nah, kami menyediakan menu baru, yaitu menu jalur riset ya, jalur riset. Jadi Bapak dan Ibu tidak perlu meninggalkan tempat tugas Bapak dan Ibu untuk menempuh program S3 ya. Tapi syaratnya lumayan gitu, lumayan. Jadi nanti bisa dilihat di website kami smits, jadi smits.its.ac.id. Dari sana bisa didapatkan info terkait jalur riset ini. Nah, kira-kira itu yang perlu kami sampaikan atau promosikan di kesempatan ini. Tanpa berpanjang lebar, Prof. Kondaher, I should say very thanks for your willingness to give a presentation about your expert. And then also for Mr. Ari, I said I would say thank you for your kindness also to present your research related to network. And I hope by having this seminar, the web seminar, a lot of collaboration can be achieved in the short period, yeah, Prof. Kondaher. And also here, the audience of this web seminar is wide. I see a lecture from university around Indonesia, so all of them are spread out among Indonesia, not just from ITS, but also from university in other cities in Indonesia. So I hope the content of this seminar can add your knowledge about computer networks, yeah, and its application. And thank you very much, all of you. That's the end of my speech. I hope everything goes very smoothly. Thank you very much. Wassalamualaikum warahmatullahi wabarakatuh.
Thank you very much, Dr. Purnama, for your opening speech. And for the audience, keep updated on our webinar series or subscribe our YouTube channel, F-ELECTICS ITS. So we will start the presentation with Dr. Kondaher Solihin. Firstly, I will read the summary of his CV. Dr. Kondaher Solihin is an assistant professor in the Department of Computer Science, California State University, Dominguez Hills. He graduated with a bachelor's degree in Computer Science and Engineering from Ahsanullah University of Science and Technology, Dhaka, Bangladesh. Then he obtained his master's degree in telecommunication from New Jersey Institute of Technology, New Jersey, USA. And he obtained his PhD degree in electrical engineering from the same institution, New Jersey Institute of Technology. His research interest is primarily in the field of network measurement. He's also interested in IP and indoor geolocation and cloud computing. And today, he will be sharing with us his expert opinion on the improvement of delay estimation over end-to-end paths. So keep updates, stay tuned in. With that, I ask that you give your full attention to Dr. Solihin, get a comfortable place to sit, avoid backlighting, and click the mute button. If you have any question, you can type it in the Zoom chat or in the YouTube comment, or maybe you can raise your type your raise hand icon. So we'll start. Please welcome Dr. Khondakher Solihin.
So I share my screen?
Yes.
Okay.
Can you?
Yeah, I'm just figuring it out. Can you see?
Yes.
Okay. So first of all, I would like to thank everybody for the kind introduction. And I also want to say thank you to Dr. Purnama for inviting me to this webinar series. I also want to thank the entire audience, which includes the faculty members across Indonesia. So today, I'm going to be talking about my overall research that I have done in network measurement. And this is the outline that I have for today's presentation. I will start off with a very brief introduction of my research expertise, network measurement. Then I'm going to talk about the topic of today's presentation, improvement of delay estimation over end-to-end paths. In this segment, I will be talking about the conventional way of delay estimation and then pinpoint a source of error that degrades delay estimation performance. Then I'm going to talk about a scheme for measuring a delay-related parameter to improve delay estimation performance. Then in the next segment, I will talk about one of my most recent research outcome. Before finishing the talk, I will talk about my new direction in research. My idea is that at the end of the presentation, I will take questions. However, if you have any question, please feel free to interrupt me. I will try to answer to the best of my capacity. Now, network measurement is basically used to characterize the internet environment. Internet is the primary communications infrastructure nowadays, which can be defined by means of various network parameters. For example, oftentimes it will be useful to know the capacities of the links that constitute the physical infrastructure of the internet. Here, I'm talking about link capacity and its measurement. Some other time, I may want to know how much of a delay an application packet requires over an end-to-end path. Here, I'm talking about the delay and its measurement. Now let's take a more practical example. Assume that I'm watching a YouTube video on my laptop station. To better utilize my time, I'm also thinking about downloading a very large file from the internet. So the goal is that I'm going to be running two different applications at the same time in parallel. Therefore, there is a possibility that my user experience in watching the YouTube video will be degraded, and that can only be determined if I know the amount of unused capacity that I have on the link that connects my station to the internet. Here, I'm talking about available bandwidth and its measurement of wireless links. So using these three examples, all I was trying to establish is that network measurement is about determining the qualitative state of the networks so that we can provide the best possible user experience and use the network resources in an optimal manner. So far, I have just mentioned about three network parameters. There are actually many more. And all these parameters can be estimated by means of two broad measurement methodologies: passive measurement and active measurement. If I'm measuring a parameter through passive measurement, then I'll collect data samples from the ongoing data traffic over the path that is under test. To do so, I will connect specialized hardware equipment to the point of measurement. That means I require a very high level of infrastructural support and administrative access to the networks. We also have to understand in passive measurement the data sample is relatively large. Therefore, I'll be using a complex statistical inference technique to come up with a measurement estimate. Now, if I estimate the same parameter through an active measurement, then I'll have a client software process and a server software process running on the end stations of the path, for example, the source and destination nodes, where the software processes will exchange synthetic packets. We also call it as probing packets to generate data samples. In this case, the data sample is small, therefore the scheme is simple. On top of everything, I do not require a very high level of infrastructural support and administrative access to the networks. And that is the reason why active measurement is more popular than passive measurement. For the remaining portion of my presentation, my focus will be primarily on active measurement. Now, to be more precise, it will be on the active measurement of end-to-end delays over internet paths. I already mentioned about delay. Let me reiterate it one more time. So delay or one-way delay refers to the amount of time a packet requires to travel between two end stations. And this parameter is conventionally estimated by means of a tool called ping, which is universally available in all operating systems. The figure on this slide basically illustrates a ping-based delay estimation between the source and destination nodes that are connected by means of a single link. Here, what happens is that the source node generates a ping packet and then send it down through to the link. Before sending it down through to the link, it puts a timestamp on it. The packet travels along the path and received by the destination node. The destination node puts another timestamp on the packet. Now, from the difference of these two timestamps, we will be able to estimate the delay over the path. But if we look into the technical definition of one-way delay in RFC 7679, which is request for comments, we will realize that one-way delay is determined by only three network parameters. For example, transmission time, which is dependent on the capacity of the link, propagation time, which is dependent on the distance between the source and destination node, and finally queuing delay, which is dependent on the amount of cross traffic along the path if there is any. Now, if you look back into the figure one more time very carefully, we will see that ping-based delay estimation has additional parameters in it. For example, host time at source and host time at destination. That means ping-based delay estimation is erroneous. So my motivation here is that I will be improving ping-based delay estimation first by measuring host times at the end station, then deducting these values from the ping-based delay estimates. So I will be talking about a scheme about measuring host time, but before going there, I want to spend some time talking about the utilities of accurate delay estimation because this is important. Here I'm going to giving you three different examples. Number one, accurate delay estimation will be very useful in high-speed local area networks. If you just have 2 microseconds of host time at the end stations, ping-based delay estimation will have an error up to 9% if we consider a single 100 Mbps link. This error would increase up to 16% if we replace the link capacity with 1 gigabits per second. Now, the second example is coming for financial trading. Accurate delay estimation can increase customer confidence in financial trading or electronic trading, which is highly delay sensitive environment. The knowledge is that if we just have 1 microsecond of added delay, it can incur a huge amount of monetary loss for the financial institutions. Now, the third example is more practical and prevalent, and this is IP geolocation. This is basically the same application that we also carry on mobile phones that pinpoints the geographic position of a network device using triangulation method. So what we do in IP geolocation is that we use 3 different reference nodes to measure delays towards a target device. Then using the delay values, we draw concentric circles to identify an overlapping region, which provides approximation for the geographic position of the target node. But the precision of the overlapping region will be degraded on the order of 200 meters per 1 microsecond if the delay estimation is erroneous. Now that we know some of the utilities of accurate delay estimation, let's look into the scheme for measuring host time that can improve delay estimation over end-to-end paths. But from this slide on, I'm not going to be using the term host time. I will replace it with a more technical term I have coined as packet processing time, or PPT. And the definition of PPT is something like this. This is basically the interval between the arrival of a data packet in the network interface card and when this is being timestamped by the operating system of the receiving end station. The figure that we are seeing here is basically the same figure we have seen before on one of the previous slides. However, here the end stations contain more detailed information in reference to the network architecture because it's showing 4 different layers. Now for this conversation, let's not worry about the network architecture. I'm just going to tell you that layer 4 is the operating system, whereas layer 1 is the network interface card. Now, it may seem that measurement of PPT is very simple because all we need is 2 timestamps from layer 1 and layer 2. And from the difference of the 2 timestamps, we will be able to approximate PPT. But measurement of PPT is a very complex business, let me tell you. For example, commodity workstations only provide timestamping facilities at layer 4. It does not provide timestamping facility at layer 1. For the sake of measuring PPT, let's say at the destination, we can instrument the destination node with a specialized network interface card at layer 4. Then we will get 2 timestamps, one at layer 1, other at layer 4. We take the difference and we have the PPT value. But the problem is the timestamps generated at layer 1 and layer 4 will use 2 different clock sources. That's why we will end up getting into a problem known as clock synchronization. And clock synchronization is one of the hardest problems to solve in computer science, electrical engineering, and also in physics. Let's be optimistic. We can still solve the problem, but the question still lies in the case when the destination node is remotely located in reference to the source node when they are connected by means of a multiple hop path. How are we going to measure PPT on the destination node? To answer this question, I have come up with a solution, and the solution is something like this. What I do is that from the source node, I measure the capacity of the n-link L sub n, which is basically the link that connects the destination node to the end-to-end path. And for the measurement, I use a probing structure. Also, I have to tell you that once I get the n-link capacity, I extract the PPT value from the n-link capacity value for the destination node. And for the measurement of the n-link capacity and eventually the PPT, I use a probing structure or packet pair structure. I call it as compound probe, consisting of a large heading packet PH followed by small trailing packet PT. For the measurement of PPT over multi-hop path, it is a requirement that my compound probe would arrive over the path at the destination node without any kind of dispersion. That means I do not want any kind of separation between the last bit of PH and the first bit of PT. To maintain that, I have a mathematical model that can identify the required sizes for PH and PT for an end-to-end path. And when I use those sizes, the compound probe does arrive at the destination node without any kind of separation. I call that configuration as back-to-back arrival. And then the measured interprobe gap from the timestamps generated by the destination node for the last bit of PH and the last bit of PT becomes proportional to the transmission time of the trailing packet. It also becomes proportional to the capacity of the n-link. So the equation at the top portion of the slide basically models the measured interprobe gap at the destination node for the compound probe. It consists of 2 parts. The first part is basically the transmission time of the trailing packet, whereas S sub t is the size of the trailing packet and C sub n is the capacity of the n-link L sub n. And the second part is basically delta PPT. I call it as differential PPT. Now, if you look into the figure on the bottom left-hand side, you will kind of realize the differential PPT is basically the variations in generating the timestamps for the heading and trailing packet. For measuring PPT, what I basically do is that from the source node, I send 2 different compound probes consisting of different trailing packet sizes, for example, S sub 1 and S sub 2 to the destination node. The destination node receives the compound probes and timestamps them to measure the interprobe gap. And when I plot the measured interprobe gaps against the trailing packet sizes, I get a linear relationship like this, where the slope value gives me the estimation for the n-link capacity. And the offset provides me information of the differential PPT. But the thing is that I don't want to measure differential PPT. I want to know the individual packet processing times for the heading and trailing packet at the destination node. To do that, what I do is that I'm going to fast forward here. I'm going to give you the idea is that I consider a first in, first out queuing model at the destination node as it is receiving the compound probes. I also consider the sizes of the heading and trailing packets, including the inter-arrival of the two compound probes, to determine or calculate the upper bound packet processing times for the trailing and heading packet respectively. Now that I have a scheme, I have tested my scheme in a testbed environment. You are seeing a figure of a 4-hop end-to-end path between the source and destination node. Here, the destination node is the node under test. To emulate real-life environment, I induce two cross-traffic flows on the second and third links along the path. These cross-traffic flows have been generated using a traffic model known as CBR, or constant bitrate traffic model, where the packet sizes range between 64 and 128 bytes. The amount of load that I am generating on the second and third link varies from 0% to 95%, corresponding their capacities of the links. This is basically my skeleton of my end-to-end path in the testbed scenario. To measure PPT at the destination node, I have designed 4 different path configurations by varying the capacity values of the links along the path. And I call these path configurations as C110, C200, C300, and C400. When I'm talking about C110, I'm referring to the first path configuration with an n-link capacity. Here, n-link is L sub 4. Of 10 Mbps. When I'm talking about C200, I'm referring to the second path configuration with an n-link capacity of 100 Mbps. So you basically understand I have measured or evaluated my scheme under 2 different transmission speeds and the n-link, which is 10 Mbps and 100 Mbps. In terms of the sizing of my compound probes, I'm using around 1500 bytes in the heading packet. This is the maximum packet size that I can use on the internet. For the trailing packet sizes, I'm using 87 bytes and 112 bytes respectively for S1 and S2. I estimated, or I measured PPT at the destination node in Linux environment using 2 different commodity workstations, Dell Dimension 3000 and Dell Inspiron 531S. I call them as D3000 and the i531S respectively. You can find the detailed specification of these workstations in the table at the bottom of the slide. The only thing that I want to tell here to conclude this slide is that my scheme is simple enough to measure PPT of commodity workstations without any kind of instrumentation. Now, when I was introducing my scheme for measuring PPT, I mentioned that one of the requirements is that my compound probe would arrive at the destination node with a 0 dispersion gap, so that the measured interprobe gap will be proportional to the capacity of the n-link. On this slide, I'm presenting data samples to show the quality of my measured interprobe gap. And the data samples have been collected on the second path configuration. And the data samples have been collected using 500 compound probes for each trailing packet sizes. If you look into figure A, graph A, this basically shows the measured data samples under 0% cross-traffic loads over the path. And as you can see, the distributions of the data samples are clustered together, and they are unimodal distribution with single peaks. I also have to mention that the solid and the dashed lines correspond to the data samples for the 87 and 112 byte packets in the trailing packet. I also have two vertical lines. They basically refer to the theoretical gap for the 87 and 112 byte packets. Now, in the distribution, the peak values are different than that of the theoretical gap or theoretical value. And this is expected because these basically correspond to the differential PPT. Now, the data sample that I've collected here is in a benign environment because the cross-traffic load is 0. Figure B shows the data samples that I have collected under 60% cross-traffic loads on the second and third links over the path. And we see that in terms of the distributions of my data samples, they're again tightly clustered. They're unimodal with single peaks. But the thing is that we have some outlier values on the right-hand side of the graph. These values correspond to the cases where some of the compound probes got caught up with cross-traffic packets in between the header and trailing packet. That's why the measured interprobe gaps were way larger than the theoretical gaps. I have a data filtering scheme to clip or filter these outlier values, and when I do that, the filtered data set from figure B shows something like what we are seeing in figure A. So they are basically the same. What I'm trying to say here that my scheme uses a packet pair structure which is robust enough to arrive at the destination node over an end-to-end path irrespective of the traffic conditions. And this helps me to measure PPT with higher consistency and accuracy. Now let's look into the measured PPT values. This table summarizes the measured PPT values for D3000 and I531S. In this table, I have columns PPTH and PPTT. They refer to the packet processing times for the heading and trailing packets respectively. For the ease of the representation of my data, I have included another column. I call it as PPT average. This is basically the average PPT between the heading and trailing packets. If you look into the table carefully, we will find that under 10 Mbps, the measured PPT on both workstations is around 20 microseconds. If you look into the measurements under 100 Mbps, these values are around 5 microseconds. Now the question is, are these values consistent? So I did a separate set of experiment in the internet environment using two internet paths, one from New Jersey to New York, other from New Jersey to Taiwan, using the same workstations, and I found that under 10 Mbps, the measured value is again around 20 microseconds, and under 100 Mbps, the values are around 5 microseconds. So I don't have any problem with the consistency. It seems that the quality is very good. But the question is that since I'm measuring a parameter, what is the accuracy or the error rate? Now, to determine that, I have measured ground truth or actual PPT at the destination node using a validation scheme that I have designed. And when I compare the ground truth PPTs with the measured average PPT values, I found out that under 10 Mbps, the error rate is around 20%, which is not bad. But around 100 Mbps, the error is around 60%. Now you can really ask me why the error is very, very, very high. I'm going to tell you in this aspect is that this is the first scheme that that can measure PPT over multi-hop path or over single hop path. And I argue that the large high error in my measurement is actually coming from the validation scheme that provided me the ground truth PPT. Let's look into the validation scheme. This slide basically illustrates the experimental setup of my validation scheme, where the destination node is directly connected to the source node by means of a single link. This link is also connected with a hardware sniffer workstation by means of a wiretap. Hardware sniffer workstation is basically a commodity workstation which is equipped with an NDES DAX 7.5 G2 card, which can generate timestamp at layer 1 at a very high speed and high precision. And the precision is 7 nanosecond. Now to determine the ground truth PPT at the destination node, what I do is that I exchange ICMP or ping request and reply packet between them. During the exchange process, I generate timestamp using the sniffer workstation to emulate as if I'm generating a timestamp for the request packet when it is just entering into the destination node, and for the reply packet when it is just coming out of the destination node. So when I take the difference of these two timestamps, I get an interval that contains the PPT for the request packet, PPT for the reply packet, including the generation time of the reply packet. I can basically discard this generation time because during the exchange process, I generate timestamp at destination node at layer 4. So when I do discard the generation time and divide the remaining gap by 2, I get an approximation of the ground truth PPT at the destination node. In this ground truth PPT, there is a simplification or assumption that the PPT for the request and reply packet are symmetric. That means they are same. That's why I'm dividing by 2. Maybe the error in my values on the previous slide is coming from this simplification, but my argument is that the error is actually coming from the packet generation time. Based on a prior research by a team from University of Southern California, they showed that packet generation time for ICMP packet is highly variable, and this value can be as big as 500 milliseconds. So that's why my scheme based on compound probe seems to have very large or high error rate under 100 Mbps. Now, if you don't have any question about packet processing time measurement, I'm going to go to the next segment where I'm going to introduce my most recent work or recent research outcome in queuing delay measurement. I already mentioned about this parameter. So queuing delay is basically the waiting time of a data packet inside a network router. And this is considered to be a dynamic network parameter. To elaborate more on that, let me use these 2 illustrations that I have on this slide. If you look into the left-hand side figure, it basically shows a router I consisting of multiple links. At this instance of time, this router is carrying a single traffic flow coming from the input link L sub n, making exit to the output link L sub 0. So when a packet from the flow arrives into the output queue of the output link, this packet will be immediately transmitted out to the output link. There will be no waiting time. So at this instance of time, the router will have a 0 queuing delay. But if you look into the right-hand side figure, the same router at a different instance of time is carrying 2 traffic flows, making exit to the same output link. And the input links are L sub n again and L sub 1. So when the packet P1 arrives into the output queue, it encounters a cross-traffic packet C1. Now, P1 has to wait for the cross-traffic packet for its chance for transmission to the output link. At this instance of time, router I has a queuing delay, which is proportional to the transmission time of the cross-traffic packet C1. Now we know what is a queuing delay. How do we measure it? There are actually several schemes available and they can be again categorized under passive and active methods. Let me first talk about few passive methods. The most popular one is router instrumentation-based method, which is widely used by internet service providers. What they do is that they connect specialized hardware equipment to the input and output links of the router, collect large amount of data sample. then calculate the queuing delay. But the problem with this scheme is that this performs single hop measurement because we need access to the router under test. Then we also have traffic analysis based scheme. This is similar to router instrumentation based scheme. However, it requires additional information. For example, what is the traffic model of the flow? What is the packet loss probability? Using this information, it can come up with or predict the queuing delay for the router under test. Same problem with this. It's another problem is that it can measure the parameter in single hop. The most recent passive measurement that I can think of is based on SDN based solution. And from the name, you kind of understand this is its scope is very limited. That means architecture specific. It can only measure queuing delay on routers in software defined networks. In terms of passive measurement, path share is the oldest and the most widely recognized tool. It uses ping or ICMP packets, individual packets, and send these packets from the source to each and every router along the path, and then measure one-way delays in hop-by-hop manner. Then it looks into the variations in the measured one-way delays to estimate queuing delay over the end-to-end path in a hop-by-hop manner. That means it will be able to extract queuing delay on each and every router along the path. The problem with path share is that it uses ICMP or ping packets, and they are not the representative of data packets on the internet. We also have network tomography based solution for measuring queuing delay, but they are topology specific, means that they can measure queuing delay on routers that are shared by more than one end-to-end links. And we have to have access to these links to perform the measurement. SING is the most recent and simplest measurement scheme. It also uses ICMP packets and send the ICMP packets into each and every router along the path, but they send, instead of individual packets, pairs of packets. Then they look into the variations of the measured interprobe, the gaps to estimate the queuing delay along the path. Now, if you want me to summarize all these schemes or methods in a single sentence, I'm going to be telling you that all these schemes require a large infrastructural support and administrative access to carry out measurement. My motivation here is that I should come up with a scheme, or I should have a scheme that can measure the parameter with least amount or least level of infrastructural support and administrative access to the networks. So I have designed a scheme. Let me give out first the basic principle considering single hop scenario. Let's say I want to measure queuing delay on router I, and I have access to the input and output links. So what I do is that I send compound probe with a different configuration in the sizes, meaning I will send a small heading packet followed by a large trailing packet, so that when the compound probe is transmitted out to the output link, I will see a dispersion in the interprobe gap. That means the last bit of PH and last bit of PT. And I'm going to call this gap without any kind of cross traffic during the passage of the compound probe as expected gap. And this expected gap can be calculated ahead of time if I know the sizes of the heading and trailing packets, and if I know the capacities of the end links. But this is a simplified scenario. If the compound probe, when it is making exit to the router, is encountered with a cross traffic flow, there is a possibility that my heading packet may get caught up with a cross traffic packet. And when both the PH and PT is transmitted out to the output link, we will see a compression in the measured interprobe gap. Now, if I can measure this smaller or compressed interprobe gap and compare with the expected interprobe gap without cross-traffic flow, we can basically measure queuing delay, because the decrement in the smaller interprobe gap will be proportional to the transmission time of the cross-traffic packet. So this is my basic principle in single hop scenario. I have extended this idea for measurement over multi-hop path. Here you are seeing an n-hop path between the source and destination node. The challenge in this type of multi-hop measurement is that the link capacities along the paths are heterogeneous. To tackle this problem, I have further modified my probing structure. My probing structure here will be that I will be having a large TTL control redundant packet. I call it as PR ahead of the PH and PT, that means the compound probe. And the size of the redundant packet will be larger than the combined sizes of the heading and trailing packets. Now this figure shows an illustration of what happens when I'm measuring queuing delay on router I using my compound probe with the redundant packet. What I do is that I send a compound probe headed by a redundant packet from the source to the destination node, where the TTL value is set with I. So the compound probe will travel along the path. At each and every router along the path, the TTL value will be decremented by 1. So by the time it arrives at router I, TTL value will be dropped so that the redundant packet will be dropped, and then this will give the chance for the heading and trailing packet to have a decompression. At the same time, if we have a cross-traffic flow, the chance is that we will have a decompression because PH may get caught up with the cross-traffic packet. But we have to understand we don't have access to the link L sub I plus 1. So when we measure the interprobe gap on the destination node, I get a cumulative queuing delay information starting from router I and up to the very last router, which is router n-1 that connects the destination node to the end-to-end path. That means to measure or identify the individual queuing delay at router I have to have the queuing delays in the subsequent routers. So what I do for multi-hop measurement, I measure queuing delay and hop by hop manner, and I start with router I-1, that means the farthest router that connects the destination node to the end-to-end path. Once that is done, I measure queuing delay on router n-1, then n-3, until I reach to the very first router, 1, which connects the source node to the end-to-end path. I have to tell you, there's a limitation on this scheme. And the limitation is that I need to know the capacities of each and every links along the path so that I know the expected interprobe gap without cross traffic on each and every router. But we should not be considering this as a limitation, because there are many schemes available to readily measure link capacities along an end-to-end path on the internet. I have evaluated my queuing delay measurement scheme in simulation environment, and you see a 4-hop end-to-end path on this slide where I have set the link capacity values to 100 Mbps. To induce queuing delay, I use traffic flows on each and every router. I have tested or evaluated my scheme using different types of queuing delays on the routers. For this presentation, I'll be only talking about the asymmetric queuing loads that I have generated. Asymmetric means I have different amount of queuing delays induced on router 1, router 2, and router 3. And the values here are 11 plus minus 9, 8 plus minus 8, and 6 plus minus 7 respectively. When I'm saying plus minus 9, I'm basically referring to the standard deviation of the induced queuing delay. And the first number is the average queuing delay. For measuring queuing delay on each and every router, I'm using 64 bytes in my heading packets. This is the smallest packet size that I can use on the internet. And I use 4 different trailing packet sizes, starting from 800 up to 1500 bytes, to see like what is the performance if I use different sizes in my compound probes. And for the trailing, the redundant packet, I'm using the required largest packet over the path. For each and every trailing packet sizes, I'm using 1000 compound probes to measure queuing delay on each and every router. Now, this slide basically shows the measured queuing delays on router 1, router 2, and router 3. The blue circles represent the average queuing delays measured by my scheme, whereas the red boxes represent the actual queuing delay that I have induced on these routers. Now, if you look into the average value, you may say the values are not same, so maybe the accuracy is not good. But we have to understand queuing delay is a dynamic network parameter. So I'm going to be looking into the ranges of values measured by my scheme, which are identified by the blue whiskers around the average value. And if I compare the ranges of values measured by my scheme with that of the actual values, I can see there's a high degree of overlap. And since there's a high degree of overlap and queuing delay is a dynamic network parameter, I will consider my scheme accurately measures queuing delay over end-to-end path on each and every routers. So this will basically conclude my discussion about my recent research outcome. Let me conclude by talking about my new research direction, to be specific for the packet processing time. I want to measure PPT at the destination node using virtualized environment. Virtualization, because virtualization is a very important concept nowadays, and it is prevalently used. I also want to see if this is possible for me to measure queuing delay of wireless workstations, because it has never been done before. In terms of queuing delay, you kind of understand that I have evaluated my scheme only in the testbed environment. My goal is that, and this is a requirement in the field of network measurement, that I perform testbed and internet evaluation. And once that is done, this is my hope that I will be able to implement my scheme at the system level, so that people can measure queuing delay readily using commodity workstations. Now, let me tell about the most recent research topic that I have got interested in, and that is in privacy policy. I'm studying the different privacy laws that has been enacted in different parts of the world. For example, in Europe, in North America, and also in South Asia. I'm also studying the privacy compliances of different websites from 10 different sectors in 3 South Asian countries, India, Bangladesh, and Pakistan. And my idea is that over time, my research topic will grow, and I'm hoping that this coming up with new ideas will happen from collaboration with students and faculty members from Indonesia, specifically from ETS. With that, I'm going to say thank you very much for bearing with me. Now, if you have any question, I will be very happy to answer them. Thank you very much one more time.
Thank you very much, Dr. Khandakhelsalihin. I think we'll hold the question and answer after the second presentation. But for the audience, if you have any question, feel free to ask. Silakan Bapak Ibu, jika ada pertanyaan, silakan ditulis di chat Zoom, atau mungkin nanti bisa raise hand, atau mungkin kalau gabung di YouTube bisa ketik di komennya YouTube. Sekaligus menginformasikan untuk kehadiran, silakan mengisi daftar hadir, sudah saya tulis di chat linknya, jadi untuk mendapatkan sertifikat dan materinya. Thank you, Dr. Khandakar Solihin. Very interesting topic on packet processing time and keying delay measurement. Maybe we can collaborate after for website privacy policy in Indonesia, Southeast Asia. It's very interesting. So the next presentation is from Dr. Ari Mazaruddin Siddiqui. Dr. Ari is an assistant professor in the Department of Informatics, Institute Teknologi 10 November. He obtained his bachelor's degree in informatics from Institute Teknologi 10 November. Then he graduated with a master's degree from Monash University, Australia, and he obtained his PhD degree from University of Western Australia. His research interest lies in the field of wireless sensor networks, data mining, and graphs. And today he will be sharing with us his expert opinion on an effective placement strategy to quantify small leaks in water distribution network. Same as before, I ask you to give your full attention to Dr. Ali. Please welcome Dr. Ari Siddiqui.
However, I think my research is still relevant to the current development of water leak detections. Okay, I'll just gonna start my my screen. Hang on a second. Okay, can you all see my screen now? Yep.
Yes.
The presentation. Yep.
Yes.
Okay, good. Right. Good. Okay. The title of my research is an effective sensor placement strategy to quantify small leaks. Sorry, to quantify small leak in water distribution networks. This is me and my two supervisors, Professor Rachel, and also Professor Amitabha. My research was funded by the Ristek Dikti from Indonesia and also from CRC for water sensitive cities. This is a government institutions which are concerning about the methods to handle or to minimize the loss of water, because in Australia, water is very, is very priceless, because we don't have, the Australian, they don't have much rainfall every year. So they have spent a lot of efforts in conserving water to prevent the water from being lost. Right, I'll start from the motivation of my research.
Dr. Ari,
yep.
Mohon maaf, mungkin display settingnya bisa diubah ke full, soalnya ini belum.
Oh yeah. Okay, I might not be sharing the correct screen. Okay, I want to maybe screen 2. Yeah. Is it a full screen already?
Yes.
Is it already full screen? Yeah, good.
Yeah.
Right. I'm using 3 screens, so I'm a bit confused. Okay, I'll continue my presentation. The first is motivation, which I've already mentioned before. It is about how to prevent water to leak during the distribution of the water from a reservoir or from a water utility to the customers. As water is not much in there, we don't have much rainfall in Australia, so they spend a lot of efforts in doing this, including the funding as well. So millions of dollars are available for research in preventing water losses every year. Okay, that's the motivation, and then related works, some related works I will present, and the gaps in between the related works, and how to characterize the signatures, the link graph, which is the main product of my research. And sensor placement strategy is the method that I developed using the link graph. Some results, some experiment results, and last one is conclusion in future works. Okay, to continue, the motivation of my research. There are basically two types of leaks. First is the big leaks, or the other name is called as a burst. As you can see on the bottom of the figure here, the bottom figure, this is called a burst. This type of leak thrusts a lot of water in a short amount of time. So this is like maybe it can be more than 2 liters per second or 3 liters per second. And so we've got a lot of water losses in this situation. However, there's a good thing. This is not a good one, but there is a good thing in this type of leak, which is we can easily pinpoint, or we can easily find out this kind of leak. Yeah. Okay. Second type of water leak is small leak, like the one in here on the figure on the top. So the small leak, it might not be as much as the big leaks. However, this leak is very hard to detect, especially if this type of leak occurs in underground pipelines. So we can't basically see it, but the water keeps flowing out of the water distribution, these networks. You can imagine if we have not only one leak position, but also in several positions, and they keep on going throughout the years. And astonishingly, the amount of water, the amount of wasted water from this type of leak, the small leak, is much more larger than the big leaks. It is because they can't be seen. They are not, they're very hard to detect, so they can last for years. So that's the motivation, the importance of the research, why small leak is very important research field to be investigated. So our goal is to detect and locate the small leaks. The term for this is quantification, leak quantification, which means to detect the presence of leak and also to find or to locate the leaks. However, there is a significant constraint in doing so. Why? Because we don't have many sensors to be placed in our water distribution network. It is an ideal thing that we place sensors on every pipe, so we can really capture the data. If there is a leak, then we can locate the leak easily. But it is impossible, or maybe I should say it is not feasible for us to do so, because it will cost a lot of funding. And for sensor provision, the sensor itself, I have spoken to a water utility in Indonesia. One sensor will cost us like about 10,000 Australian dollars, so 100 juta rupiah. So it is very expensive one. Therefore, we need to find a method to optimize or to maximize the functionality of the limited number of sensors. So that is the question, the main question of my research. Right. Some related works are the PUDAR and LIGAD research is the initial research in leak detection. This is a research in 1992, if not 1995. So it's quite long time ago. However, this research keep on growing and still an open research field for researchers to conduct research in that. The PUDAR and LIGAD research, they use only mathematical modeling to observe flows and pressures, and using that mathematical modeling to find the leak locations based on the differences between their models and the actual observations on the field. Rachel is my supervisor. Rachel's research is to also predict the leak size and also to locate the location. However, Rachel's research and PUDAR's research, they only use a small networks. When their research are expanded to larger network sizes, it will take a lot of computations and also problems with accuracy as well. Some other research on the other rows here, they observe big leaks. As I said before, big leaks are easy to find out compared to small leaks. So this is to strengthen the gap of research that I have done compared to the other research, and also to strengthen the importance of my research. In summary, my contributions are to quantify small leaks, which is to predict the size and also to locate the position of the leak. For this, we develop a sensor placement strategy, which is to model a leak signature as a unique directed acyclic graph, or DAG. Then we clusterize the water distribution networks. After we model the water distribution network into a graph, a big graph, and then we clusterize that big graph into smaller areas, and then we place sensors at the inlet of each cluster. Right, before we proceed, I'd like to mention about the water balance law. Basically, if we have a water distribution network, consider this figure on the right side as a water distribution network. This is a small example. We've got 10 liters per second water coming into the system from a reservoir, and then there are two demand points, 5 liters each. Therefore, 5 plus 5 equals to 10. So this is considered as the water balance law. What goes in equals to what goes out. However, what happens if this situation occurs? The amount of water coming into the system is 11 liters per second, but the recorded demands are only 5 plus 5 equals to 10. So we suspect there is a leak in the system that consumes 11 liters per second, but the recorded demands are only 10 liters per second. The challenge is, where's the leak? Right. Now, in order to find out the location of the leak, we need to characterize the leak first. We use a modeling. There's a famous software among the civil engineers. It is called the EPA-NET. The EPA-NET is a free software and modeling that we can use to generate to generate or to run water distribution system operational settings. Right. This figure is an example of a running or operational water distribution network, and then we simulate that water distribution network using the EPA-NET, and then we've got data out of the simulator, pressures and flows. We took a snapshot of this water distribution network. As you may have aware that the consumption of water, the diurnal consumption, a daily consumption, might vary in the morning, in the afternoon, in the evening, and in the night. We took this snapshot of this situation in a water distribution network where demands are at the lowest condition. So normally researchers take the snapshot during the night, maybe 4 to 5 a.m., where people are fall asleep and there's not much water to be consumed in this situation. Why we do this is because during the minimum demands, if there is a constant consumption of water going into the system, this might be suspected as leaks. But we can't do this in the daylight because there are some variations and also legitimate water usage by the customers that are flowing constantly. We can't consider this as leakage, but we can do that in the night during the term for this is the minimum night flow. So where the demands are very limited or nearly zero. So we can say that if there is still constant flow, we can consider this as a leak. Then we simulate leaks at every position, at every possible positions. In this case, we simulate leaks at every nodes. We call junctions. Nodes or junction are just the same thing. And then we compare the flows of the normal situation compared to the leak situation at every case, at every location. And then we record the magnitude and the direction, the magnitude, the difference of flow in pipes triggered by leaks at different positions. For example, this table here, suppose there is a leak at junction 244, pipe 823, 826, and so on will give us a range of flow differences triggered by the leak at junction 244. And we continue this, we do this to every leak, to every possible leak position in that network. And then we record and store the data in a table. We call this table as the influence matrix. So as you can see here, every leak position contributes or triggers different flow differences, different delta flows in each pipe. Therefore, we can consider this as the signature of the leak. As I said before, if we have sufficient number of sensors, we can just plant those sensors into every pipe in a system, in a water distribution system. We will have this table, and then had a leak occur in one position, we can just easily to find out where the location is. However, this is not possible, as I said before. We only have a few number of sensors to be placed. So the mission is to find which pipe to be placed, to be used to place sensors, the most strategic pipes in a network where sensors are supposed to be placed. Okay, now, okay, the beaker might be too small for you to look at. So we model a water distribution network as a directed acyclic graph. As you may see here, in a water distribution network, there is no such cycle water flow. The water flow in a network must end at one point or several points, but there's no such cycle. Therefore, we can model this water distribution network as a directed acyclic graph. That is the basic line. Now, from the influence matrix before, from here, we can transform that matrix into a graph. Here, you'll see J or junction or node number 244. It means the leak position is here. And on the right side, the leak position is on J247. Then from the influence matrix, the data or the path are different between leaks at J244 and leaks at J247. So not only the edges are different, but also the weight of the edges are also different. The both edge means this pipe or this edge contains more water, more excess flow compared to the others. The dot lines indicate that these pipes, they don't have, they are not influenced by the leaks, by the leak at this position. On the other side, the left side of the pipe is not influenced by the leak at J247, which means these two graphs are completely different. So that's the lean graph that that is my the core of our sensor placement strategy. Okay, as I said before, the lean graph of a leak at one position is different to the other. Now, what is the limitation or the constraint when we construct a lean graph? The snapshot of water distribution network is taken at the minimum night flow, and to construct the lean graph, it has to be done using the minimum common leak. So the minimum common leak where each position of a leak has sufficient link graph that can be constructed, triggered by the leak, but also not too large where the leak signature will be indistinguishable one to another. So these two figures is an example of that situation. On the left side, the leak occurs at 0.4 liter per second. That constructs a good link graph. So the position is on the red colored ring in here. And on the right side, the leak on the same place occurs at 1.2 liter per second. As you can see here, there is an excess area triggered by a larger size. So suppose I have another leak in this position, the signature of leaks at the original position and the new position will be the same. So the leak signature is considered as very hard to be differentiated, or both of them are indistinguishable. So this situation or this explanation means that the link graph is suitable for characterizing small leaks. It can't be too large. If it is too large, then the signature will be indistinguishable. So it must be for characterizing small leak sizes. Right. Despite the uniqueness of each link graph, some of them has similarities. Yeah. The similarity of the link graphs can be used to to group link graphs or positions of leak positions with similar leak signatures or similar signatures. To measure this, we use two aspects. First is the Jacquard index. We use Jacquard index, which is the intersections of two link graphs divided by the union of the two link graphs plus. So this Jacquard index measures the similarity between edges, both the sides of the edges and also the direction of the edges, because some leaks can trigger can cause flows to change from the initial direction to a different direction. The second aspect to consider is the weight of each edge of a link graph. Therefore, we have a weighted link graph in here, and we measure the weighted link graph using that formula, the similarity of weighted link graph using that formula from every junctions in a network or from every possible leak position in a network. This is supposed to be junction number 2, not junction number 1. So there's a typo in here. As we can see here, there are some of them has more similarity compared to the others. Most notably is the similarity between junction number 2 and junction number 3, 0.89. This means that junction number 2 and junction number 3 are in a nearby location. Therefore, their signatures are almost the same. So we can group both of them and use only one sensor to represent the signature of these two locations. So that is the basic method to do so. Right, now we partition the graph. From here, we have the highest weighted index, weighted link graph similarity, and we use that edge as the centroid of a cluster. Let's say this is the centroid of the cluster. And then from that point, we set a threshold where the boundary of that cluster is to be set. Suppose we set the threshold as 0.6 maybe. So as you can see here, the edges or the junctions with the weighted score more than 0.6 will be recruited as the member of this cluster, but the other junctions with lower than 0.6 weighted line graph similarity will not be recruited, marked as the red arrows, and they will be recruited by different cluster. Then we have the cluster. We do this to every other junctions until all of the junctions are recruited or included in a cluster. Last step is to find the sensor locations. Once clusters are formed, each cluster will be connected to a different cluster by one or more than one edges. Suppose we have this cluster here, and then this cluster is connected to the other cluster by 1, 2, and 3 pipes. So there are 3 candidates to be selected as the inlet of this cluster. The inlet of this cluster can be considered as the sensor location, because that sensor location will detect the presence of leak in that area. So it must be something. It must be a position where it can represent most of the leak signatures in that area. So from these 3 candidates, we take only one of them with the highest weighted line graph similarity score. For example, from these 3 edges, the green colored line or the green colored edge is selected because it has the highest weighted index similarity compared to the others. And we do this for the other clusters as well. To examine the robustness of our method, we use 3 types of water distribution networks. We categorize the networks as small, medium, and large sizes with various numbers of junctions, pipes, and also tanks, and average connection degree. The average connection degree is the number of connected edges to a node or a junction. The more the connected edges to a node means the more possibility for water to split to the other edges. Yeah. So that means the similarity of the link graphs can be more indistinguishable compared to a network with a low connection degree. So it's quite challenging for a network with high connection degrees. Right, this is some example of our method. On the left side, the green boxes or the green colored dots indicate the sensor locations from our method. Also on the right side, there are some locations indicated or produced by our sensor placement strategy. As you can see here, the numbers on the right side, the number of sensors on the right side is, I think, more than on the left side. It's clearly that the green colored ones are more than on the left side. So it will require more sensors compared to the figure on the left side. In this situation, it might be not possible for us to provide this number of sensors. Therefore, we can adjust the number of sensors required by a network by recalibrating our algorithm to match the number of sensors. Suppose the number of sensors suggested on the right side is 10, and then we only have 4 sensors. Then we need to reduce the number of required sensors by 6. So small clusters will be merged into one and will be represented by 1 sensor only. But larger cluster will remain the same. Therefore, we can reduce the number of sensors to match the provided number of sensors. So it is quite flexible. Our algorithm is quite flexible to accommodate the needs of water utility, for example, or our research. Another thing that might come up is some locations are sensitive which means there is very little chance for us to plant a sensor in there. For example, places with strict security where we cannot access that place. It can be a government office, banks, or some other areas, I don't know. Therefore, we need to accommodate that situation as well, where we can adjust the algorithm by grouping the junctions in that area into one cluster, and then recalibrate the sensor placement. Then we have the sensor location. Once we have the sensors already placed using our algorithm, the next thing to do is to find out the quality of the placement. Two measurements we use for this, the cosine similarity and also partition balance. The cosine similarity measures the distinctiveness between any sensor's readings that are placed at the locations suggested or recommended by our algorithm. And the partition balance means it is a measurement to measure how well the balance of the partitions. For example, if we have one cluster with 200 nodes in there or 200 junctions in there, and the other cluster contains only 5 junctions, we can say that there is a huge imbalance between these two clusters. Therefore, we need to recalibrate the balance of the clusters by dividing the large sensor into smaller ones, and the smaller cluster will be merged to some other clusters to make it a larger portion. Then we find the sensor place using our algorithm. From the networks that we use, we've got cosine similarity scores and partition balance as shown in the figures. On the left side, in the middle column, the cosine similarity scores. Ceton 5 is considered as, it has a low cosine similarity. It means that the sensor readings placed at one to another, the readings between the sensors are quite distinctive. So it can distinguish the leak signatures in one cluster significantly compared to the other clusters. In here, we see also Pescara network. It has 0.09 cosine similarity. It is very nearly zero. It means that the distinctiveness of sensor reading is very high. Pescara has 3 tanks. This network has 3 tanks, which means the number of tanks also influence the distinctiveness of sensor readings, because leaks in one part can only drag excess water from a tank, or a combination of 1 or 2 tanks, or a combination of between the 3 tanks. So if you place sensor at the inlet of the pipe that connects the tank or the reservoir to a network, we will have a very distinctive readings. Partition balance is quite balanced between one network to another. What determines the partition balance, the aspect that determines most of the partition balance is the average connection degree. The more average connection degree, the more partition balance will be, because the split is quite equal from one side to another. Therefore, clustering or partitioning the network is will give us a more balance compared to network with low average connection degree. Now then, we have the sensor quality sensors in place, and then what next to do? The thing that we need to do is now to locate the leaks. That is the goal of the research. After the sensor is placed, then we need to find out the leaks using the sensors that are already placed there. For this, we created a database containing the readings of sensors, where leaks are simulated at every possible places. Yeah, and then the readings are on the right side. These pipes are the location of the sensors. So we record only flow differences in pipes where the sensors are placed. So we don't record flows in every pipe because it is not visible, as I mentioned before. We created this database. In this table, this table is suitable for leaks at 0.2 liter per second, and then we create another database containing leaks at 0.3 liter per second, leaks at 0.4 liter per second, and so on, until we have sufficient database. When okay, to find the location of the leak, we match the current reading of sensors to the database of leak signature. So we match the current readings with this. And using the Euclidean distance, we can find out which records with the lowest distance of the current readings and the records in the database. So every record in the database with the lowest distance will be regarded as leak signatures with the closest one to the current reading of the sensors. Then the location of the leak is indicated by the labels or where the leaks are simulated initially. Using this method, we have a quite accurate result for 0.2 liter per second with 5 sensors. With 5 sensors, we've got around 78% accuracy. But this accuracy gets higher when leaks are larger. Why? Because larger leaks gives us more distinctive readings in here. But remember, when the leak is too large, then the readings might not be distinguishable. Okay. Now I come up to the conclusion. We have proven that our method is effective to quantify small leaks. And because we don't use real data in here, we only use simulators. So therefore, we need to really try our method to real world data and see how possible developments can be made accordingly. Some future works also using time series data, as we know all that the water consumptions keep changing in the morning, afternoon, and in the evening or in the night. Therefore, we need to adjust with that. That is a one-day period, a one-day cycle. What about if water consumption is compared between different seasons? For example, the water consumption in spring, water consumption in summer, and also in winter, they are different. So we can't use the same data during for different seasons. So that is also another challenge for this research. Other important possible research that can be considered is the multi-leaks. So leaks can be more than one at a time. So we also need to look into this to find out more leaks using our method. Yeah, that is all for today. I think that I have. So I'm just going to end up my presentation now. So please, Dr. Agus Budiratjo, time is yours.
Thank you, Dr. Ari, for your excellent presentation, addressing critical issue and propose a solution based on a graph approach. So the next is a question and answer session. Kepada Bapak Ibu, silahkan kalau misalkan ada yang ditanyakan dalam bahasa Indonesia, enggak apa-apa, nanti saya bantu untuk translate-nya kepada Dr. Kondakhir atau kepada yang lain. Mungkin bisa raise hand. Ada yang ditanyakan? Ya, mungkin pertanyaan pertama dari Bapak Eko, Pak Eko Pramunanto. Ini pertanyaan untuk Dr. Ari Sidiki, nggih, Pak?
Yep. Can I do?
Ya, mungkin saya bacakan dulu. The first question is for Dr. Ari Sidiki. Apakah ada batasan teknologi sensornya? Is there any limitation for the sensor technology? Mungkin Dr. Ari bisa menjelaskan.
Okay, for the sensor limitation, I don't think there is a limitation for the sensors as long as the sensor is accurate. So accuracy is the most important aspect of the others. From the current sensor manufacturing, if I'm not mistaken, the accuracy is very high. It could be the inaccuracy will only like 2%. So 2% inaccuracy is very, very accurate. Some sensors, are more sophisticated sensors, will be, the inaccuracy will only be like 0.05 or something, 0.05%. So it's very accurate. Modern sensors, they also manageable through the net, but it can be more expensive. My colleague, he did a different research. He conducted research in smart meters. So that smart meter aims to characterize the differences in water consumptions throughout the day. For example, we did that research in Karata and Kalgoorlie. It is a very rapid developed area in Australia, but the problem is the water is very scarce in there. So people keep complaining about this supply of water into that area. They keep on complaining that the water is not enough for our area, therefore they require more water supply. For this, the government, if they want to meet the demands, it means they have to invest more on pipes and some other infrastructures. It is expensive, basically. So what we do is to map the water consumptions by characterizing the water consumptions. We can consider that this type of water consumptions is used for example, to water the garden, and the other pattern of consumption is used for other purposes, and so on. So what happened was, they keep on complaining that they don't have sufficient water supply from the government. It is because all of the activities they are packed into one time frame. So what they did was they issued a policy by segregating the time frame for water to be used. When that policy was applied, then they don't have the same situation anymore. They don't complain that they don't get sufficient amount of water being supplied to that area. So that is also another thing that can be recorded by the smart meter. So that technology is another level. But if you ask me about the limitation or the minimum capacity or minimum ability of the sensor, as long as the sensor is accurate in acquiring water data, either flows or pressures, I think that is still sufficient. Second is the accuracy. The more accurate the sensor, the better. So the bias or the uncertainty in providing the data is can be really suppressed, because once the data presented is accurate, the algorithm will also give you an accurate analysis. However, if the data is inaccurate, then we know the results. So that's my answer, Dr. Agus. Yep.
Thank you, Dr. Ari. The next question is for Dr. Khandakir Solihin. It's from YouTube. Dr. Khandakir Solihin used cross traffic to make the gap between head and trailer packets closer. Can you explain more? Why do you need to minimize the gap? Sorry if I missed the explanation about this. Yes, it's from the YouTube. Please, Dr. Khandakir. Sorry, I think you are still mute. To unmute.
So is this for the queuing delay measurement or the packet processing time?
There is no explanation. Kepada Mbak Virus Rahma, mungkin kalau mendengarkan ini untuk queuing measurement, queuing delay atau untuk proses packet time.
I think I understand the question now.
Yeah.
So the thing is that if I have to if I have lots of compound probe with increased gap, then the measured gap is not going to be representative of the transmission time of the trailing packet. Then I would not be able to estimate the capacity of the end link. That will lead us to like wrong calculation of PPT. I think the question was for PPT.
Okay. Thank you. Thank you for your answer, Dr. Solihin. And the next question is for Dr. Ari. Thank you for your insightful presentation. Considering the characteristic of the object being studied, leak in water pipeline, is there other object, for example, electricity or gas pipeline, where your solution can be applied?
Yeah. For the gas pipeline, I think it is quite similar to water, but we really need to think about the modeling as well, because my approach is still in modeling phase, so we need to also consider the mathematical calculation as well. But for the electricity, I think this one is more challenging, because planting sensors for electricity is I have no experience in this, so I can't really answer for this. But for gas pipelines, I think it is possible, as long as we use a correct sensor. The characteristics of water and gas are similar. Once they leak, then they're gone. But for the electricity, determining the location of leak is a bit challenging for me. But if we have a method, a correct method to characterize the leak in electricity, I think this method can be also possibly can also be applied. It depends on the sensor basically. Once the data is obtained, then we can do the analysis. Yep, that's my answer. I hope this suffices.
Thank you. There is a next question for Dr. Khandakir Solihin. Is the routing experimentation using only one path from source to destination, or is there any alternative path?
In this case, can you repeat the question again? I'm sorry.
Yeah. Is the routing experimentation using only one path from source to destination, or is there an alternative path?
Routing, yeah. This is just one single path, but for the travel of the probing packet, because when I'm saying that I'm measuring queuing delay of a path consisting of 4 routers, then I'm considering that the routing path is not going to be changing. And the other thing we have to understand when we do like any kind of network measurement, we consider the path is stable for some period so that we can do the measurement. Otherwise, it's impossible to measure if the packet is changing routes to go to the destination. That's a very good question, yes.
Thank you for your answer. And the next question, it's for Dr. Ari. Please explain more detail for calibration process, and would you like to show me a picture of or link for the sensor, please?
what was the first question?
The first question is, please explain more detail for calibration process.
Calibration of what?
I don't. There is no.
Okay, calibration. Maybe about the sensor itself. Some sensor needs more calibration. Some sensors they adjust themselves based on the data that is provided by the manufacturers. But for the sensor itself, there are some available sensors online. As I said before, one of the most sophisticated sensor is will cost us like $10,000 or something. That gives you the ability of the sensors to record the data and also maybe to give you some alert if the water consumption is a bit out of normal situation. But yeah, there are some sensors. There are some references for that. I maybe I can give you after this even the references later on.
Thank you, Dr. Ari, for your answer. So the next, it's for Dr. Salehin. What will be in the future research that we here in ITS could also collaborate with?
Well, there are many possibilities. I mean, in terms of if there is a network testbed, we can do the experiments, or we can come up with completely new topic. We can start working on it. So it's about the, like, if we have the desire or if we have a like good topic.
Okay.
Because when we do like experiments on like in a computer networks, we always do not have to do experiments. We can start off with simulation. Simulation can produce good data as well.
Okay. Actually, I have a question for Dr. Salehin. It's for from me. I read your paper and the recent paper on simulation study of measurement keying delay on IEEE. And in the future work, you mentioned that there are possibility incorporating an advanced technique for filtering the data sample by designing an intelligent data filter technique, like using machine learning based solution. Do you mind to explain it globally how it can be done?
Can I? I'm sorry.
Yes, I read your paper, and in your paper, in the recent paper, you mentioned that for filtering the data samples, we can use machine learning based solution. Do you mind to explain it globally, how it's done?
Well, I mean, my idea is that right now, when I'm measuring it, I fix the several parameters in the probing phase. So it's quite deterministic. What I want to know, like, if this is possible to come up with a method where I can change the dynamics of my measurement real time based on the performance, so that I can get the optimal measurement values. Because the queuing delay is a highly dynamic parameter. It changes over time. And even if it doesn't change, like, measurement of queuing delay is very complex because there are many other things that are related to it. So that's why I was thinking, if there's a possibility, we can find a machine learning method when I'm saying, okay, what is the gap that I should have, or what is the frequency that I should have for sending the probing packets to the path, or what are the sizes, as I just mentioned, that I should have. And if we reduce this, sizes in the probing packet still get a very good measurement value, then basically we are reducing load in the network. So if you put too much load in terms of probing packet on the network, that load may affect the actual data traffic. And if there is too much load, packets will be dropped, the performance of the real data will be affected. That is one of the downside of active measurement. So we have to identify what is the balance.
Okay, that's great. Thank you very much for your explanation. Is there any question? Another question, maybe? Let me see. Is there any? I think that's all for this morning, for today's webinar. So thank you for all your questions. Before we close this webinar, I'd like to ask Dr. Salehin and Dr. Ari to give your closing remarks. Firstly, please, Dr. Salehin.
Okay, again, I'm going to say I'm very happy to be sharing my knowledge, my little knowledge with everybody. And I'm open to any kind of communication in terms of research, like a personal connection. We can talk about anything. We can talk about, I mean, maybe food. What's the best food that I should eat when I'm going to Indonesia or when you're coming here? But the thing is that the main idea is that I want to present myself in such a way that you feel that I'm accessible. So send me an email if you have any question. I will try to accommodate as much as possible. And if you want my email address, if you search my name, you will find the email address on my website. I also have a LinkedIn account. You can communicate through LinkedIn as well. I'm looking forward to meeting new people from ETS and other universities in Indonesia. Thank you very much.
Thank you, Dr. Salehin. Maybe I will share also your website in searchgoogle.com.
Thank you. Yeah. But in case you want to know my email address, I'm writing it down in the chat.
Okay, that's great. That's great. Thank you. And please, Dr. Ari, for the closing remarks.
All right, closing remark would be thank you for Dr. Kondaswari for joining us here, and also for having me in this very exciting webinar, as I say, because through these kind of events we can share our knowledge. Although this is an ongoing process, I can't say this is a final product. This is still an ongoing research, and it will keep on growing and growing. And I'm open for collaborations with researchers and also from the practitioners from water utilities, of course, because my research is mainly about it's mainly about detecting leaks. So yeah, I'm sure there will be some more opportunities for us to collaborate in the future. Also for our students, maybe if you are interested with my topic and also Dr. Kondai's topic, we can start working on together maybe to find out more things that we need to that we can do and that we can find out. I think that's all, Dr. Agus. Thank you for your time.
Thank you very much, Dr. Ari. Yes, I hope it will be a stepping stone for us and open new research collaboration. So I would like to thank our two special speakers for your wide insight, to the audience for participating since this morning, and to the Faculty of Electics who have organized this event. Further information for the certificate and the slide will be delivered to your email account. Don't forget, mungkin saya jelaskan dalam bahasa Indonesia. Jangan lupa untuk mengisi daftar hadir agar dikirimkan materi yang hari ini dan untuk pengiriman sertifikat digital. Thank you for your attention. Good morning. Assalamualaikum warahmatullahi wabarakatuh.
Thank you. See you later. Bye.
Bye. Bye.